So 2A2 is about the gas state. You lost your what? The gaseous state can be effectively modeled with a mathematical equation relating various macroscopic properties. Gas has neither definite volume nor definite shape. Because the effects of attractive forces are minimal, we usually assume that particles move independently. Okay, when you go to the notes page, I got a whole bunch of fantastic links on here. Of course, the biggest one we're going to deal with in this unit is dV equals nRT. Now, I'm not going to do a whole bunch of calculations for you, because I would hope in your previous chemistry class you already did a bunch of these, right? Okay, so there's a few on the problem set just to refamiliarize you with them. All right. If you have any problems with those ones from the problem set, then definitely ask about it next Wednesday. Okay? Part A. Cedric.
Ideal gases exhibit specific mathematical relationships among the number of particles present, the temperature, the pressure, and the volume.
Everybody know that, right? And we know where it is on our equation sheet, right? Right. And we talked about what R is all about, yeah? Okay, so be very careful when you're using this that you're sure that whatever units are in the R that you're using, whether it's 0.0821 or 62.4 is the other one they give you? All right. Make sure that your other quantities match those same units. Otherwise, you're going to have problems. B. Abdallah.
In a mixture of ideal gases, the pressure exerted by each component, the partial pressure, is independent of the other components. Therefore, the total pressure is the sum of the partial pressure.
So, because the gas particles are not interacting with each other, we can basically assume that if I plug in a number of moles for one component, and the temperature and the volume, and I solve for the pressure, if I do that for another component in the mixture, however many moles it has times the temperature, which should be the same, right? And the volume should be the same if they're in the same container. And basically what we get is two different pressures. Two different pressures as if the substance was acting all by itself. As if it was the only substance in that container. Okay, what I mean is, here's my container. And it has some number of particles in there moving around, bouncing off each other, doing all the things that gases do. And it exerts some pressure, P1. And then if I think about removing these and putting some other gas in there, and it's going to be moving around and colliding and causing its own pressure, right? We could calculate the pressure with this substance, pressure 2. When I put them both in the container, the total pressure is just going to be the sum of each individual pressure. We call these partial pressures. Okay, so the equation, Dalton's law of partial pressures, is that the total pressure is equal to the sum of all of the partial pressures. We're going to use that in the lab that we're going to do next week. In the lab we're going to do next week, we're going to measure a gas, but the gas we're going to collect is actually a mixture. And so we'll be able to figure out the total pressure. We'll be able to figure out one of these partial pressures, and we'll have to use Dalton's law to figure out the pressure of the other. Okay, that'll make more sense when we talk about the lab on Monday. So yeah, this is called Dalton's law of partial pressures. Is this on your equation sheet?
Yes.
Where is it?
Yes.
Right below Pupner?
2 below.
2 below. Ooh, yes. The one below that is actually kind of interesting as well. It's sort of a related version of this.
Below which one?
The one right below Pugner. It says the pressure of A is equal to the total pressure times what? Times X sub A, which is?
That's so confusing. Why do they put a multiplication sign there at all?
Here?
Yeah.
What do you want to put?
Nothing? There's no multiplication signs in PV plus NRT.
That's true.
Or maybe they would think that you would think that the X was a multiplication sign.
That's probably why. Right? So if the total pressure is the sum of all the partial pressures, and we know that the partial pressures are related to how many moles are in there, then it would make sense, for example, if gas 1 was exerting 1 atmosphere of pressure, and gas 2 was exerting 2 atmospheres of pressure, so that the total was 3 atmospheres of pressure, it will make sense that the pressure of A is the total pressure times the fraction of particles in there that are A particles. Right? Think about the example I just said. If the total was 3 atmospheres, and let's say 1/3 of all of the atoms in that container were A, and 1 mole of A for every 3 moles total, that's going to give us a partial pressure of A of 1 atmosphere. Okay? So the partial pressure of each component is proportional to how many moles there are in there. Right? The mole fraction, if you will. Okay? That's pretty straightforward. Okay, C. Sadia.
Graphical representations of the relationships between P, V, and T are useful to describe gas behavior.
All right, so I put some graphs on there. Here's the pressure versus volume graph. What kind of function is this? That's an inverse function, right? If PV equals nRT, if we keep these constant, then as P goes up, V should go down. As P goes down, V should go up. Right? So this sort of behavior here is characteristic of an inverse function. Although if I graph other quantities like volume versus temperature, I'll see a direct relationship. Because they're on opposite sides of the equation, if I keep everything else constant, as V goes up, T has to go up. Pressure versus temperature should show the same relationship. As temperature goes up, everything else being constant, pressure should go up. Right? N versus either of these things should be linear as well. If I put more moles in there, the pressure should go up if the volume is constant. Right? If I put more moles in there and try to keep the pressure constant, like in a balloon, if I have a flexible container, then more moles should equal more volume. Right? The more moles I pump into the balloon, the bigger the volume is going to be. Okay, the only one that has that inverse, well, I guess moles and temperature would have an inverse relationship as well, right? Although that one's a little bit harder to conceptualize. But pressure and volume for sure. The more I decrease the volume, the higher the pressure. The more I increase the volume, the lower the pressure.
How would you conceptualize moles versus temperature?
I don't know. As soon as I said that, I was like, crap, I hope nobody asks.
Mr. Well, you knew that I was thinking.
I know. Just thought I'd weasel my way out of it. More moles equals lower temperature?
That doesn't make sense.
That doesn't make sense, right?
I feel like when you had more, they would bounce around off of each other more than these guys.
Okay, but the problem is, in order to look at just the relationship between the moles and the temperature, you have to keep everything else constant. So you have to have a constant volume and a constant pressure. So let's say we're at 1 atmosphere and a 1 liter container. If I put more moles in there, we know the pressure is going to go up, right? How do I keep the pressure constant?
You have to raise it proportionally to this?
Raise what?
Pressure proportionally?
No, I'm saying I want pressure to be constant.
Change the volume.
I want the volume to be constant too. We're just trying to look at the relationship between moles and temperature. And I said that should be inversely related. Right?
So how do you keep it constant?
How would you keep pressure and volume constant? Well, having a non-flexible container would keep the volume constant, right? But in order to prevent the pressure from
Does
increasing,
that mean a vacuum?
no. Remember when I put the liquid nitrogen in the balloon and it started expanding? Okay, well, what would happen if I had put that in a non-flexible container? Eventually the pressure would have gone up and it might have exploded, right? How could I have prevented it from raising its pressure?
Decrease temperature.
Decrease the temperature. If I put more moles in a container, in order to keep the pressure constant, I have to cool them down.
Oh.
If I take moles out of a container, in order to keep the pressure constant, I have to increase the temperature so that they're moving faster and hitting the walls with more force.
That wasn't that bad.
That wasn't that bad. But yeah, I had to think about it for a second. What? How the heck? It's because you have to keep the pressure constant, which is the hard part. In order to keep the pressure constant, you have to be changing the temperature. And if you think about it that way, it makes sense why there's an inverse relationship between moles and temperature.
If you increase the size of the container, would pressure just decrease also?
You're keeping everything else constant?
Yeah, but if you increase the size of the container.
As the volume of the container goes up, the pressure goes down. Okay? Now, those are mathematical relationships, but we also need to understand them from like a theoretical perspective. What are the particles actually doing to make those relationships true? So part D talks about kinetic molecular theory. Kinetic molecular theory, combined with a qualitative use of the Maxwell-Boltzmann distribution, it's like my seventh best friend, provides a robust model for qualitative explanations of these mathematical relationships. So let's first talk about the kinetic molecular theory. I've got a link here. This first one is the good one. Kinetic molecular theory is 5 postulates, 5 little ideas that if they are true, then a gas will behave like an ideal gas. So these 5 things have to be true in order for something to obey the ideal gas law, PV equals nRT. Mia, read number 1 for me.
Number 1. Oh. A gas consists of a collection of small particles traveling in a straight line motion and obeying Newton's laws.
What are Newton's laws?
Drawing blanks right now.
What?
We're drawing blanks. F equals ma.
F equals ma. So if you apply a force, you get an acceleration, right? Every action
As a reaction.
has an equal and opposite reaction, right? So when the particles collide, they can do something to each other, but they still have to obey Newton's law. The force on one particle can be applied to another, but that's going to change its acceleration, things like that. 2, Lindsay.
The molecules of a gas occupy no volume. That is, they are clean.
Molecules of a gas have no volume.
So they don't know what the volume is.
They don't have any volume.
Isn't
They
that
are
possible?
one-dimensional objects.
How is that possible?
That's not possible. This is not true in real life.
Oh.
We're going to talk about real life equations, okay? This is not a real life equation. This is the ideal gas
So
law.
then why do we use it if it's not real?
Why do we use it? Because it's a nice, simple thing to start with to explore relationships and to do calculations based on them. And it does a pretty decent job under certain conditions of predicting what pressures and volumes and things like that a gas is going to have. Okay. Same reason you Learn to ride a bike before you learn to ride a motorcycle. Motorcycle is much more complicated.
But,
It's much harder to ride a motorcycle.
whoa.
Have you ever
Those are
rode-
two different things. When you're riding a bike, you're not riding a motorcycle incorrectly.
Okay, same reason you learn to ride a tricycle before you learn to ride a bicycle.
Well, like when
When
you
you're
do
riding a
physics
tricycle,
about
you're not riding a
friction, you just
bicycle,
think that there's no friction and physics
Yeah.
problems first, and then you take it.
It's because if I show you the equation that actually takes into account the size of the particles,
Does it get really ugly?
well, not ugly. It's not too bad. Some of them get really ugly. Some of the equations get really, really nasty. But, let's see, this is the ideal gas law. There are several equations for real gases. The one we're going to talk about is the van der Waals equation. Van der Waals. The van der Waals equation we actually say that the volume that the gases can occupy is not just the volume of the container, it's the volume of the container minus the volume occupied by the particles themselves. N is the number of particles, right? B is their bigness.
Seriously, their bigness?
No, their size. Their molar volume. But it's related to the size of the particles. I always just say it's the bigness because that helps me remember. B is the bigness. Oh, that's related to the size of the particles, related to their volume. Okay? Now I'm going to add something else next to the B, but I'm not going to do it yet because we're going to keep talking through kinetic molecular theory. Number 3! Tina!
Collisions between molecules are perfectly elastic. That is, no energy is gained or lost during the collision.
Okay. So when particles collide, they do not lose any energy. They just bounce off each other. Sorry. There's no overall gain or loss. So the sum of the individual kinetic energies of the particles before the collision is the same as the sum of the kinetic energy of the particles after the collision. One could gain, then the other one's got to lose. Okay?
So it's like
Conservation of energy. Yeah. In reality, there's a possibility that when particles collide, they could give off some, maybe some infrared or something. Maybe when they collide, they start jiggling. We know when particles jiggle, they release infrared radiation, right? So that would be a slight loss in energy. I was waiting for somebody to react. I'm just sitting there going like this, and Lindsay's just like, I'm not even acknowledging you, Bull. I'm not playing that game. Okay, Deanna, number 4.
There are no attractive or repulsive forces between the molecules.
You believe that?
No.
Yeah, maybe if we had done 2A first, you'd say, oh yeah, why would they attract each other, right? But we did 2B, we know about intermolecular forces. Do intermolecular forces go away when we create a gas?
Nah.
They just get weaker.
They do not get weaker.
Oh, they just atoms are farther apart, or the molecule.
The atoms are farther apart, so they don't experience that force as much, okay? When they come together, they may still have some attraction. But usually, remember if we think about that Lennard-Jones, that sort of like well thing, and the simulation where I could put those two atoms together and pull them apart? If I were able to throw those atoms at each other really quickly, they're going to go down through that well and then right back out. Okay, so usually they're moving fast enough that those attractions don't last very long. There's not enough time for the particles to actually interact with each other. Okay, that's in an ideal gas. We assume there's absolutely no attractive or repulsive forces. Like I guess there'd have to be repulsive forces. They bounce off each other, right? Okay.
You don't get repulsive forces.
But it's not like there's.
You don't get repulsive forces in things like that.
Why would it bounce?
Yeah, how would they?
Well, why would it stick? If there's no attraction.
If there's no attraction, it wouldn't stick. But if there's no repulsion, it would just
What
go
would stick?
right through the other particle.
Well,
It would just
How
stay
would
in
it
one
go
place
through
if
the
there
other
was no
particle?
repulsion.
I mean, if I'm hitting these, they're not electrostatically repelling. Well, they are sorry. They're not like magnetically repelling each other, but they are actually, all their little electrons are getting too close together and causing repulsion, which then makes them fly apart. Right? I can't imagine how things could repel each other could bounce off each other without repulsion. Okay? You don't like that, I don't care. There's no, just gonna assume there's no intermolecular forces. Let's just talk about that, okay? But in the van der Waals equation, there are. Okay? And we have to account for the attraction between those particles. So there's actually a term here that accounts for how much the particles attract each other, but it also depends how close those particles are to each other, right? We just said the closer the particles are, the more they experience that attraction. The farther apart they are, the less they feel that attraction. So N over V is related to how closely packed the molecules are. The more molecules, N, there are, and the smaller the volume, V, they are, the more this term is going to matter. Okay, and if we think about solving this, when we didn't have a P, let's say we plug in this other stuff and we solve for some P, and let's say it's 1 atmosphere, right? Well, in the van der Waals, P plus this thing is 1 atmosphere. So when we add this in and we try to solve for P, we're going to have to subtract this from both sides. So the pressure is actually going to be slightly lower. Van der Waals would predict a slightly lower pressure because of this term right here. Because if particles need to bounce off each other and then go and fly in the other directions to hit the walls of the container to create the pressure, if they're too busy sticking to each other, they're not going to be out there flying and hitting the walls of the container. So the more the particles stick together, the less pressure you actually get.
why don't you take into account repulsive forces?
Again, that's the thing I don't like about number 4. I think there has to be repulsion for the particles to bounce off each other. We know because of intermolecular forces are all overall attractive. There's no force that causes more repulsion than attraction between molecules at large distances. At close distances, when we get those inner electrons to start to get too close together, then they repel. If the nuclei get too close together, they will repel, right? So there's always that repulsion there. But what we're worried about is, when are there attractions? If there are attractions, it's going to slightly lower our pressure. I don't know if I answered your question, but I'm moving on. Lindsay? Please do. Okay, now there were some equations that I skipped over, or sorry, a graph that I skipped over here I'd like to come back to. This is a graph that shows us the difference between real gases and ideal gases. I think, well, yesterday we were playing with Dippin' Dots, but at one point when I was talking about the gas constant, I explained that really it's a ratio of PV over NT, right? And it happens to be 0.0821 for most gases, okay? Now, they've arranged this a slightly different way. They've said PV over RT, okay? And they're saying for an ideal gas, it equals 1, okay? So if we think about plugging 1 mole in there at maybe a standard temperature and pressure or something like that, right? It shouldn't really matter what the temperature or what the pressure is. We should still get the same ratio of those quantities, right? But this graph shows you some real gases, N2, CH4, H2, CO2, and it shows you that as the pressure increases, we get some deviations from ideal behavior. And it's sort of weird because at first, the ratio pressure volume over RT appears to be lower than what an ideal gas would predict. But then eventually it jumps up and it's higher than what an ideal gas would predict. Why?
Bigness.
Bigness.
This is where it crosses the axis, or where it crosses like where the ideal axis is.
Good question. I'm not sure. I'm not sure if it has physical significance or not. The places where we're lower than expected must be due to attractions. Anytime you're getting less pressure than you would expect, well, the pressure's on the top here, right? PV over RT, okay? So I know this is saying the pressure atmosphere, okay? I guess maybe at these high pressures, maybe you get a slightly different value of one of these other quantities, okay? But for this thing to dip below what an ideal gas would be expecting, I would think that's because of the attractive term, right? If the particles are actually attracting each other, then they'd be exerting less than expected pressures. Or they might occupy less than expected volume, right? If the volume of the container, if it's flexible, is dependent on how many particles are hitting the outside of the container, then if the particles are attracting each other, they're not hitting the outside of the container, making the volume slightly less. Okay, so I think these are dipping below the line because of their attraction. Does that make sense? Well, if we think about what we learned in the intermolecular forces unit, which of these particles has the strongest intermolecular forces? Don't everybody answer at once.
What was the question?
Which of the
Which
of the gases shown here
All right.
would have the strongest intermolecular forces?
CO2.
N2.
3 different answers. And you said N2. Why?
That's a good question. Because
'Cause you had a
oh,
one
N2
force-
has the triple bond.
Yeah.
What does that mean about H2O?
Oh, okay. All right. I don't know. So it's wrong.
CO2,
So just says CO2. Why?
because it's polar, and it has
Because it dips the lowest on the graph. You said it was attractive.
Wrong.
Isn't it bad?
No, it's linear.
You said it. You
High
said the
bond.
dips are attractive forces. So if that one dips the lowest.
Well, right. So yeah, CO2 dips the lowest, so it probably has the strongest intermolecular force. But if we didn't see this dip, would we predict that? CH4 is.
Polar.
Man, you guys gotta learn those polar, non-polars. What's the shape here?
No.
Tetrahedral.
Tetrahedral. Non-polar. These are all non-polar.
Oh, it's the size, whichever is biggest.
Who's the biggest?
CH4. No.
CO2.
wait. No, CO2. Yeah.
H's are really small.
CO2. I think it said something, yeah, it said something in our outline about the strength of the London dispersion force increasing with polarizability, which is related to the number of electrons. So CO2 is going to have more electrons than CH4, so it's going to be more polarizable. So the London dispersion here is going to be stronger, which is why it's dipping lower than the rest of them, right? Then I would say CH4, then probably N2. H2 is going to be the weakest intermolecular force. Apparently so weak it never sees that low deviation, okay? Why are they above the line over here? Probably from the bigness, right? If we're getting these pressures, really, really super high pressures, the particles have got to be really close together. And if they're really close together, they're really going to be running into each other. Right? In order to get that high of a pressure, you really got to crunch this thing down, and now you're talking about the volume of the container is maybe approaching the volume of the particles themselves. Maybe there's just a little bit of extra room, and so then the size of the particles is really making a big difference there. Okay?
Will it keep going up as you keep increasing pressure?
I would think so.
How high can you increase pressure? Like, what's the highest pressure?
Where it becomes a solid.
Is that what pressure does? Is adding more pressure make it like a liquid?
Yeah, I mean, eventually, if you look at phase diagrams, eventually as the pressure increases, you're going to change phases and things like that. So you might turn it into a liquid and then a solid. You could still exert pressure on a solid. Is there a highest pressure? I mean, pressure's probably pretty high in a black hole.
Probably.
Probably.
What's the pressure like in
That's sort of gravitational,
What's
though.
the pressure like in the room?
Pressure in the room? 1 atmosphere. You ever felt 1 atmosphere of pressure?
Yes, right now.
You're feeling it all the time, right? Well, yes, but you got holes in your body. Those holes in your body let that pressure inside of your body, so you got 1 atmosphere of pressure on the inside of your body and on the outside of your body, right? You got that 1 atmosphere of pressure is pushing on the bottom of your arm and on the top of your arm, so there's some balance, right? There is a way to feel, to get some sense of how strong that 1 atmosphere of pressure actually is.
Correct.
Since we're on the topic, let's try it.
Wait, don't you do like a, is it with a vacuum and like a trash bag? And you like sit.
Hey, don't ruin
Okay,
it
I'm
for
sorry.
everybody!
Oh,
Mia!
I've seen a video.
Wait, do you
Okay,
sit there?
I'm
How do you
done.
breathe?
Your head's like sticking out, and he like takes the pressure out, so it tightens around. So you're in the trash bag, and you're like, it's like your head just showing, and he vacuums out all the
And
pressure.
then it's literally
Yeah.
just like a mold
Yeah.
of
Do
your
you like
body.
this
I
one?
remember seeing it. Citra, small person.
Has anybody never done this experiment before?
I've seen him, I haven't done it.
Vienna!
I did it at work.
A healthy volunteer. Come on up.
Go to my young habitat.
Are you gonna just like?
Are all your affairs in order? You have your will's all set just in case this experiment goes wrong?
I guess.
You don't have anything to... Hold on. We're going to go over here.
Okay.
Lindsay, move here. All right, step inside there, will you?
I call it.
First time in a trash bag?
Yeah.
Okay. Squat down a little
Not
bit.
my first time.
Can you kneel down?
Yeah.
Excellent. Perfect volunteer. Okay, now, you're going to hold this, and you have to hold your hand over this a little bit, because you don't want the bag to suck onto it and stop it. So kind of hold it by your stomach and hold it like
Okay.
Now right now, the bag has 1 atmosphere of pressure on the inside, it has 1 atmosphere of pressure on the outside. So she's not feeling any overall force from the bag. But what we're going to do is we're going to suck some of the air out of the bag. Then there's going to be less collisions with the inside of the bag than there is with the outside. So the increased collisions on the outside, she's going to experience a force inwards. You ready?
Okay.
Stand up. You can't stand up. Stand up. What? It's strong, right?
Yeah.
And I maybe reduce the pressure on the inside by 5 or 10%. If I decrease the pressure on the inside 100%, if there was a vacuum on the inside, it would crush your bones. Because what's atmospheric pressure? You can come on. What's atmospheric pressure?
The weight of air.
1 ATM. 1 atmosphere. What are some other units?
Torr.
Torrs in millimeters of mercury. That is the amount of mercury that the atmosphere can hold up in a little tube, okay? Anybody ever heard of this unit?
SI.
PSI.
Bike tires.
What does it stand for?
PSI.
Pounds per square inch.
Oh, yeah.
Oh, yeah.
Atmospheric pressure exerts 14.7 pounds of force on every square inch of the Earth's surface.
Did Americans come up with that and then they were very salty and they didn't want to get rid of it?
Yeah. They're like, we don't want to do kilopascals
Oh, I remember Pascal. Pascal's trying to put
or newtons per square meter, which kilopascals are related to. Okay. How many square inches do you think were on the outside of your body?
8 watts.
A lot, right? Probably more than 100 square inches on the outside of your body, right? If you think about a postage stamp, you could probably cover your body with 100 postage stamps. 100 times 14.7, that's 1,400 pounds of force on the outside of your body. You think that bag was crushing you with 1,400 pounds? No way, you would be hurt. It'd be like having a car on you, right? So I didn't suck out anywhere near all of the air out of the inside of the bag, okay? But the atmosphere is actually exerting quite a bit of force on you. But again, that force is balanced on tops and bottoms, inside and outside, so we're just used to it, we don't normally experience it, right? If you were to get jettisoned up into outer space instantaneously right now, all the gas that's inside of your body that's normally under atmospheric pressure suddenly then expand, your eardrums would blast right out of your head.
Oh, because it's inside going
Gas
out.
that's,
Right.
gas
Okay.
that's
And the same
dissolved
thing-
in your blood would form bubbles.
Same thing going like underwater. Right?
Yeah, look up explosive decompression if you want some gory details about what might happen.
They did that Mythbusters.
Did they?
With it was like a train. It was like oil tank.
Oh,
Yeah, it exploded.
Yep.